Hey everyone, it's Mr. Ray here with our next calculus lesson. This will be our third lesson in the curve sketching. First lesson we looked at critical points. Second lesson we looked at asymptotes, which was a review from grade 12, advanced functions. Today's lesson is brand new stuff, and it's based on the second derivative. Second derivative gives us some more interesting information about what the graph will look like. So the lesson is called concavity and points of inflection. So what we're actually finding when we do the second derivative are these things, the points of inflection. So we'll talk more about what those points mean and how they relate to concavity. Okay, so this is basically using second derivative. Okay, and if you remember, I guess about 3 lessons ago, we did a lesson on velocity and acceleration, which was also looking at second derivative, so it's very much related to this lesson. Remember, if you had a function based on the position or distance of an object, based on time, the first derivative of that function would be the velocity function based on time. And if you took the derivative of the velocity or the second derivative of the position function, you'd be actually you'd have an acceleration equation based on time. Okay, so we're going to be looking at the second derivative. It's still combining stuff we did in the first lesson. Not so much today on the second lesson on asymptotes. That will be all brought together in the next lesson, which is the final lesson. So there will be one more lesson this week, and that'll be the final lesson in curve sketching. That'll be released Thursday morning, and then there'll be an assignment based on curve sketching. Okay, and then next week, it looks like there's 3 lessons for that unit. So I'm not exactly sure. I'm going to take a look at it. I think it might be too much to try to jam 3 lessons in 1 week and then an assignment. So I might do 2 lessons, and the following week the 3rd lesson on the Monday, and then probably I'll release the assignment early, like say Wednesday, and have it due on the weekend, so you'll have lots of time for that, and then the course will be done. Okay, so let's get back to the lesson. So in terms of the notation for second derivative, we've seen this before when we did velocity acceleration. Second derivative has the double quote, f double prime x or y double prime, or this Leibniz notation. I just want you to be able to recognize, again, we talked about that with the velocity, d2y over dx squared is the same thing as the second derivative in the function notation. All right, so point of inflection, that's really what this lesson's all about. It's a point on a function where the slope of the tangent changes from increasing to decreasing, or from decreasing to increasing. So what does that look like? Okay, well, before we talk about that, I want to talk about these 2 things, and this relates to concavity. So concavity means it could be concave up or concave down. Okay, very simple explanation here. Interval of a graph of a function is concave up if it looks like a smile. So basically it could be something like that, like a parabola opening up, and if it's concave down, it looks like a frown. So it could be a parabola opening down. Now, it doesn't have to be this complete parabola shape. It could be parts of the parabola. So I could say, well, this shape here, if I just stop it right there, that's also concave up. And this shape here, which would be the second half of this parabola opening up, this is a 3rd type of concave up. All 3 of these are, well, you could consider a smile or parts of a smile. but they're all three considered to be concave up. So that's important because when we're finding points of inflection, it won't necessarily look like this. In fact, it won't look like this. It'll be one of these two things or one of these two things, where if I split the concave down into two separate parts, so it could be that, it could be that, or that. So those are the three options for concave up and three options for concave down. So what's a point of inflection? Well, basically it's where it changes, where the graph changes from either concave up to concave down, or vice versa. So what you could incorporate different parts of that. So you could have a graph that looks like, actually I'm going to do it down here. You could have a graph that looks like concave up to that point, and then from there it looks like concave down. Okay. So this point here, where it changes from concave up to concave down, would be the point of inflection. You could also have the opposite, where it starts off as concave down, and then at that point there it changes to concave up. Of course, it keeps going. So that's exactly what this point here says. Graph of a function f of x is concave up on an interval. Oh, sorry, that's not it. A point of inflection is a point on a graph where the function changes from concave up to concave down. So that would be concave up to concave down, the first one, or vice versa, concave down to concave up. So both of these points where that change occurs, these are called the points of inflection. I like to put POI on here, but people might think it's point of intersection, which is not. So these are the points of inflection here. So these two here. Okay, so very important. It's basically where the graph changes from accelerating to decelerating, or vice versa, in terms of acceleration velocity. Okay. Let's see what this is. Now, how do we find these points of inflection? Well, this is where the second derivative comes in, because just like we found critical points by setting the first derivative equal to 0 and solving, to find the points of inflection, you find the second derivative, set it to 0, and those points that satisfy that would be points of inflection. Okay, so very related. So you use first derivative to find critical points, and then use second derivatives to find points of inflection. All right. Now, when we look at the second derivative, how do we know if it's, like, once we find the point of inflection, how do we know it's, you know, one of these situations, or maybe it's something completely different? How do we find out which shape it is? Well, we do interval testing just like we did for critical points. So if I'm going to look for a range of values for x, and if the second derivative for that test value is positive, that means it's concave up. If the second derivative is negative for that value of x, then it's concave down. So we're going to apply this basically for the interval test for concavity to see, okay, once we found the points of inflections, how do we know what's going on to the left and right of those points? Okay. Now this one here, this can be confusing because the second derivative test is different than what we just talked about. So we use the second derivative to find the points of inflection, and then we look at the interval to the left and right to see if it's concave up to concave down, or vice versa. But this thing is different here. So second derivative test is not what I just talked about. Okay, and you could get through life never actually needing to use this. This is kind of like an alternate test. Now, what this test is for, if you remember back from lesson 1, once we found the critical points, we did interval test to the left and the right, found out if the function's increasing or decreasing, and that told us, oh yeah, it's a it's a local min or it's a local max or it's neither. If you hopefully remember that. Now this second derivative test is an alternate for that, and to be honest, sometimes it doesn't work, and you have to do what we did already. So I just want you to understand what this is for, in case you're asked to do it on an assignment question, or maybe in the homework. Okay, so how do we use this? Well, if I find, now this, I had to correct this. So if we found a value of c, like a value c for x, which basically c would be a critical point, so f, the derivative at c is equal to 0. So once we found that c is a critical point, what we can do is then plug that value of c into the second derivative, and if the value is positive, then that critical point at c is a local min. If the value of f, the second derivative at c, is negative, then c is a local maximum. Now, however, it can fail. If the second derivative, you plug c in, you get 0 again, then the test fails. So you have to go back and do the first derivative. Okay, so hopefully that makes a bit of sense. If not, maybe just rewind this a bit. But this is kind of an optional thing. You don't have to use it to do a perfect graph, but you still have to know what the purpose of this thing is and how you would use it. Okay, so but if you do any assignment questions that doesn't ask to use the second derivative test, you're not expected, you don't have to, but you can if you'd like. Okay. All right, so I've got, I believe, 4 examples to look at, and this lesson can be confusing, so it's definitely tougher than the first 2 lessons of this unit. So it might take a couple of iterations of this to wrap your hand around this new idea of points of inflection and concavity and how you actually use that. Okay, so first question here, there's a typo here as well. That should be a plus 10. Okay, it says sketch the graph of this. So we're gonna do the first derivative and second derivative, find out those key points, and then hopefully do a half decent sketch. So first thing we're going to do is take the derivative of f of x. So that's going to be 3x squared minus 6x minus 9. Okay, so what we're going to do now is we got the first derivative. We're going to find the critical points, and hopefully from that find local mins, maxes. So we set this equal to 0. Now at the same time, I'm going to factor out a 3. Okay, and that factors very nicely x minus 3x plus 1. And from that, I can see I'm going to have 2 critical points. I'm going to have critical points. I'm going to have one at x equals 3. I'm going to just skip to the actual coordinate here. I'm going to have one at 3 and one at negative 1. Okay, now if I take 3, x equals 3, and I plug it into the original function, I'm going to get negative 17. And if I plug negative 1 in here, I'm going to get 15. Okay, now we'll do the second derivative. So I basically start with the first derivative, take the derivative of it, I get 6x minus 6. I'm going to set that to 0. I could factor the 6 out here and find that I have possible point of inflection. We'll see if it's true or not. Point of inflection, and that's going to be at 1, x equals 1, and then when I plug 1 in here, I get the y coordinate of -1. So I got 2 critical points. They may be local mins or maxes, and this should be a point of inflection. So before I make all sorts of conclusions just based on that, I'm gonna look at some intervals based on the point of inflection to find out what's going on at that point. Okay, so this is going to be slightly different, although it'll seem similar to our interval testing for the first derivative. Okay, so for this I'm only looking at that one point and the intervals to the left and right. So I'm actually going to make a separate column for that value of x. So x equals 1, x greater than 1, and x less than 1. So I'm not testing to find out what's going on with the critical points, because if I was, I would have intervals based on -1 and 3. This interval is based on the second derivative point of inflection of x equals 1. So I'm going to put 3 rows here. Okay, so the value of f prime of x, the graph of f of x, and the sketch. I know that seems like it's the same thing. I think I took this from the textbook, so you'll see what the difference is when I do this. Okay, so if x equals 1, we already know that if we plug that into the second derivative, we get 0, because that's how we got that point in the first place. Okay, but what we're looking at on either side is what's the sign of the second derivative. Okay, so I could just take any test value here. I guess I could take 0. If I plug 0 into second derivative, that would be 6 times 0 minus 6, or 0 minus 6. So the second derivative for that interval is negative. And if I do the same thing for greater than 1, if I plug in a 2, you can see that the second derivative will be positive. Now all I do is I convert these signs from the definition of concave up and concave down. Concave down is when the second derivative is negative, so concave down. I've got concave up, and this is probably going to be a point of inflection. Okay, so just remember from the original part, the concave up, concave down looks like this. Concave up looks like this. Now, this point is between these two, so we can basically where's my picture here? It's basically going to look like this. So I'm going to have a point of inflection here. Does that make sense? Hold on one sec. Okay, so quick timeout. I had the direction wrong here. So if I'm going to join concave down and concave up, where this is on the left, this is on the right, you can see I'm going to use this part on the left. So I basically got that rightmost section, and then I stop, and then it turns into the left part of this. So the point of inflection will go from concave down to concave up. Okay. Now, so if I'm doing my sketch, okay, so I've got my point of inflection at 1. I've got 2 critical points, one at -1, one at 3. Okay, and I've got the coordinates of all these points, so this is going to be a little compressed vertically, but so be it. So I've got 3, -17, so way down here is a point. And I've got negative 115, so way up here. And then the point of inflection at 1, negative 1 will be about here. Okay. Now, they didn't ask us to really do the first derivatives, so I already know I've got critical points here. I could do the second derivative test here and plug in x equals 3. If you remember, I'll just bring that up here. So this is where you could use the second derivative test. If I plug in what I know to be a critical point into here, if the value is greater than 0, it's a local min. If the value is less than 0 in the second derivative, it's a local max. So using that, I'll figure out that if I plug x equals 3, I know that's going to be positive in the second derivative. I didn't actually do it here, but from that you can find that that's a local, that would be a local max. Yep, local max, and the second one is a local min. Now, you could have figured that out by looking at the intervals for the first derivative, but this is a way you could use that second derivative test to avoid having to create a whole table. So from that, I can now go and, I know that's a local max. I know this is a local min, and I know this is a point of inflection. So I know that's the point where it changes. You can see that this is going to be concave down on the left, and this is going to be concave up. So the best way to draw these is to actually put the points, put your little cups at the points at the local mins and maxes, and then basically you can draw that down. You have to keep it going as if it's concave down to that point, and then it changes right here. So at that point it changes and goes back up. And this one here, we didn't do any tests for x-intercepts or y-intercepts, although we do know the y-intercept would be 10 without any real work. But we do know this comes down, but based on what we've done, we don't really know what these x-intercepts are. Okay, so that's how you use the second derivative to find possible points of inflection, and then use the intervals for the second derivative to be able to sketch using concavity. So concave down to concave up looks like this. Okay, so hopefully that helps you. That is a pretty important point. I mean, we could have graphed this we could have sketched this without the point of inflection, but we're really guessing as to where this curve kind of changes concavity. And you can see that's an important point. Okay, second example. We're looking at a quartic function, so f of x is x to the fourth. So it just says sketch the graph. So first do the first derivative. That's going to be just pretty simply f4x cubed. If we set that equal to 0, divide by 4, x will be 0. So we have x equals 0 is a solution, so that's a critical point. Now if I do the second derivative, okay, I take the derivative of 4x cubed, that becomes 12x squared. If I set that equal to 0, I get the same answer. I get x equals 0 for that too. Okay, so it's a little confusing when you see this because it looks like, it shows that at x equals 0, it's a critical point and it's a point of inflection. So we have to kind of look more in detail as to what's going on there. I mean, most of us could probably know what this graph looks like. I mean, we did it in advanced functions. It's just going to be parabola-like, but flatter at the x-axis. Okay, so let's look at the intervals like we did in the first example. So it's going to be x less than 0, x equals 0, x greater than 0. So derivative, second derivative, then the graph of f of x, the sketch of f of x. So it's really to kind of come up with information that we'll need to do our actual graph down here. Okay, so we already know that at x equals 0, the second derivative is 0. That's how we figured to use this point. If I plug in like a negative value into here, well, that's anything negative becomes positive, so it's going to be positive for any negative values of x, and it's going to be positive for positive values of x. So I got the same information on both sides. It looks like concave up in both cases, unlike the last example where it changed. Now, since it hasn't changed from concave up to concave down or vice versa, we have a question here because the whole definition of point of inflection is it changes from one concave up to concave down or vice versa. So in this case, it's not changing. So it's not a point of inflection, even though it kind of told us that here, but it was confusing because it was the same. Could it be a critical point and a point of inflection? Well, this tells us that in this situation, no, that's not a point of inflection. Now we could, if we did interval testing for the first derivative, we would actually find that this is an absolute min. Well, it's a min. We could start off by saying it's a local min, and if I find the x and y coordinates for 0, it's 0, 0. Okay, and so concave up, in both cases it looks like that. Now it's not going to join at the tops like that. It's like I said, it could just be. So what I'm going to do is kind of correct this, because the only way these guys can join is if I look at the two halves, right? So I've got to the left of 0 it looks like that, to the right of 0 it looks like that, and this 0, 0 point just joins them together like this. So you can see that this is a local, well, it's a local min, but it's actually an absolute min or global min, because that's the lowest it ever gets. Okay. So that's just to show you the situation where what happens when you get the same value of x showing up for both critical point and point of inflection. So further testing is required, and you can basically rule out it can't be a point of inflection in this case. Okay. Third example, we have a cube root function. Okay, so it says sketch the graph of the function. Again, it says use first and second derivatives to analyze this function. So now remember, this is x to the 1/3. So when you're doing the derivatives, you can use the power function or exponent rules for derivatives. So I'll just jump right to the final answer. This works out to 1/3x to the 2/3. And if I set that equal to 0, well, hopefully you can see, well, this can never happen, because the only way that this could be 0 is if the top is 0, and the top is always 1, so there's actually no solution here. Okay, that's interesting. So that sort of tells us that there's no critical points, and we're going to come back to that in a minute. Let's look at the second derivative. So if I take, the derivative of this, obviously I'm going to convert it back to the negative exponent and 1/3 x to the negative 2/3. If I take that derivative, it works out to negative 2 over 9x to the 5/3. Okay, and if I set that equal to 0, you're going to see the exact same thing. This can never occur because the top can never be 0. So again, no solution here either. Okay, so where do we go from here? Well, one of the things that we've never had to look at before is critical points. Critical points occur when the first derivative is equal to 0 or when the function is discontinuous or not continuous. So we never looked at that before, but this deserves a second look, because if I write my function, if I look at that, is that function ever discontinuous at a point? And you can see, well, if x is 0, then it's discontinuous. So that's a question that you should ask, and it only comes up when you have, a rational function for your first derivative. We've never had that up till now, so you ask yourself, is the first derivative continuous? And the answer is not at x equals 0. It's continuous everywhere else. So that would be the point 0, 0 if you plug it in. So what's going on at this point? Well, this is a critical point. Like I said, critical points, we have expanded our definition of critical points. We also have to include any points of discontinuity, as well as any values of x where the first derivative is 0. So we're going to base our interval testing on x equals 0. So interval, so we have x less than 0, x equals 0, x greater than 0, and I'm going to have my 3 rows. So actually I'm only going to have 2 here, so we'll just skip that one. So I'm looking at the second derivative, and here I'll just look at the graph. So here we're looking for the sign of the second derivative. Now we already know if we plug in 0 into the second derivative, it's undefined, so it does not exist at that point. Okay, but what's going on to the left and the right? If I plug in a negative value for x into here, I'm going to get a negative value over a negative value. So overall, the function will be, second derivative will be positive to the left. And if I do the same thing for a positive value, I'll get negative over positive, which means it's negative overall. Okay, so in terms of the graph, I'm not going to do that third row. The graph, since the second derivative is positive, it's concave up. So I'm just skipping that one. And here, since it's negative second derivative, it's concave down. So this is actually a point of inflection, because that's the point that breaks the concavity between concave up to changes to concave down. So obviously it's only going to be up to this point here, and this one's only going to start there. So when I actually show the point of inflection, it looks something like this. Sorry, go the other way. It's going to look like this. Okay, and that's because concave. Okay, so let's just go to the sketch. So I've got now at x equals 0, remember it's undefined. Well, the function is defined there, but the second. So we do have the point at 0, 0. And if you Actually, I think I got that backwards. Yeah, I did. Okay, so that is going to look like this. Now this one's a hard one to draw for sure, but cube root, we're changing from this to this. And you can see this side is concave up, even though it kind of looks almost sideways compared to what we're used to. This would be concave down. So it matches up concave down to concave up like that. This is a little bit confusing, but hopefully that makes sense when you're looking at this is concave up, this is concave down. Okay, so that would be the graph, and that's your point of inflection. Okay, last question. Again, you're seeing some strange examples in this lesson of, we're not just doing simple examples that always work and basically you're just finding different values. I want to, just like the textbook does, I want to show you what do you do in the case where it doesn't look like it usually does. So these are some specific unique examples. Well, not unique, but examples where you don't do the normal process, or at least you test a little bit differently. Okay, so this says determining points of inflection on the graph f of x equals 1 over x squared plus 3. If you take the first derivative of that, I'm going to skip the whole derivative part. You're going to get negative 2x over x squared plus 3 squared. Okay, and if you take the second derivative of that, you're going to get, of course this one's going to take a little longer if you do it step by step, 6x squared minus 6 over x squared plus 3, this to the power 3. Okay, and if I set that equal to 0, I'm basically setting the numerator to 0. So that works out to 6x squared equals 6, or x squared equals 1. So that works to x is equal to plus or minus 1. If you plug these 2 points in, you're going to get negative 1 and 1/4, and 1 comma 1/4. So those are the 2 points, possible points of inflection. If you did look at the first derivative, now it didn't really ask to do this, you could see you're going to have a critical point at, if we set that to 0, x is equal to 0. So you're going to have a critical point at 0, comma, and if you plug 0 into here, you're going to get 1/3, 0, comma 1/3. So we're going to do our interval testing for the points of inflection to find out what's going on. This one's going to be a little wider because we've actually got 2 points of inflection to consider. So I'm going to have five columns here. 5 and the kind of the comment on the left side. So we've got our interval. So it's x is less than negative 1, x is equal to negative 1, x is between negative 1 and 1, x equals 1, and x is greater than 1. So you can see as soon as you have that second point of inflection, your table gets bigger by 2 more columns for each new possible value. So if I check the sign of the second derivative here, well, I know these 2 are 0 because that's how I got them. And if I plug in a value like negative 2 into the second derivative, the sign of that's going to be positive. If I plug in, if I plugged in x equals 0, I'm going to get a negative value. And if I plug in something bigger than 1, I'm going to get a positive value. So you just take test values like you normally do. You could put in x equals 2, x equals 0, x equals -2, and to get the sign. Okay. Now in terms of the graph, we've got, this is concave up, this is concave down, this is concave up. Okay, so this is a point of inflection, right? So these, because on both sides you have a different concavity. So what does this point of inflection look like? Well, it's the left side of this and the right side of this. So basically, it's going to look like, sorry, it's the right side of this and left side of this. So it's like this. And then you get the opposite going on here. So you have like a point of inflection in the middle there. So now when we do our sketch, this is a strange looking graph. It actually doesn't have any points of discontinuity because there's no value of x that will make this undefined. So unlike most rational functions, you don't have to worry about that. So in terms of the points of inflection, I've got, 1 and -1, and then I've got critical point here, and the points of inflection, so that's about a quarter, I guess. That's about a quarter, -1, 1. So we could tell when we do, when you look at this, you know that, this is not going to turn around anywhere in between here. So this actually is a local max, and you can draw it out like that to make it a parabola. And then both of these points, it changes concavity. So it actually goes out, and you do have a horizontal asymptote at the y-axis, at y equals 0 at the x-axis. So that's what that graph looks like. Okay, so I know that's a lot of pretty tough examples to consider, especially when it's a brand new topic. So I really think it's important. Try some of these questions out. Know how to use the first derivative to find critical points, see if they're local mins, maxes, or neither, and then use the second derivative to find the points of inflection, and then use the interval test for points of inflection to find out concavity for certain areas, and then put everything together and come up with a nice sketch that's got all the local extrema and points of inflection. Okay? All right. So there'll be another lesson on Thursday. All we're doing on that lesson is putting all our tools together. So I'll bring in some other stuff that we didn't really do, like x and y intercepts, but combine everything to come up with an algorithm for curve sketching. Okay? Thanks, guys.